ready for takeoff.
Right, thanks for coming, everyone. I'll get cracking. So I want to talk to you today about an idea that's been around for a while, which we can call Ruby's core gem. I'm a big fan of giving the big idea up front to get straight into what we're talking about achieving. So Ruby has a core library, right? It's those methods like, those classes like array, hash, string, that sort of thing. And currently this is implemented in C in the standard version of Ruby. So this is the code to implement loop do, for example, which is a core library routine. And you can see it's written in C, has to be broken apart into a couple of methods, because that's the way things like rescue work in the C version of Ruby. And this isn't very readable, right? This is hard for us to understand as application programmers. Turns out it's also a bit hard for the Ruby VM to understand and to do anything meaningful with. So the big idea is let's rewrite this into Ruby using the language we use for our applications. Let's use it for the core library as well. And you can already see some benefits here. This is much more understandable. If you want to know what loop do does, you can simply read this code. You can see it runs a while loop and it yields the block for each iteration. You can maybe even see some things you didn't know before. Like, did you know if you call loop without a block, it gives you an infinite enumerator? Well, you can see that from the source code, even if you couldn't see that from the C code as easily. We can also see that, can you break out of a loop do? Yes, you can. You can use the stop iteration exception. And that's clear again from the Ruby code. And it turns out this has many benefits, not only for understandability, but also for how the VM can optimize it, how you can use tooling on it, all sorts of things. And it also turns out to be a great way to talk about the potential future for Ruby and how we can make Ruby much better in the longer term. Bit of context about me and my work. I'm from Cheshire in the UK. That's Cheshire as in the cat. I've got a PhD in compiling Ruby. I founded TruffleRuby, which is an alternative implementation of Ruby I'm going to be using as an example for some of the work I talk about today. I was formerly at Oracle Labs. I'm now at Shopify, which is a really supportive place with great people. I'm interested specifically in optimizing idiomatic Ruby code. So I like talking about optimizing Ruby as it is, rather than transforming Ruby to be something else in order to be optimized. I lead a British cavalry squadron in my spare time. I'm interested in meeting other Ruby reservists and veterans if you're out there. So one of the core concepts I want to talk about is Ruby's tower of libraries. We can talk about Ruby's different sort of libraries and where they sit in a tower. So we have the language, the core Ruby language that we have in the Ruby interpreter. We can talk about the core libraries being one level above that. And then above that, we have the standard library, which is things like JSON that you can require without installing anything. And on top of that, we can talk about gems and user code. So at the bottom, we can also talk about this being Ruby code and C code. And the further down the stack you are, more stuff is written in low-level C, and the higher you get, it's more written in Ruby. And currently, the core library is written in C almost entirely. And that's what we're going to talk about today. So at the bottom, there's the language. This is a very small number of things provided by the language Ruby, the Ruby language itself. So that's things like classes, modules, methods, method calls, and some control structures like if, while, case, and, or, things like that. But it's actually a really small subset. Very little else is provided by the language. So in the code example here, we've got if and an and a method call, and that's really all the language provides. The next level up, we have the core library. This is things like array, hash, but also lower level things like numbers and strings. Numbers and strings are actually part of the core library. They're not really provided by the language. Great thing about, and also some control structures. So things like loop and array each and hash each, these are provided by the core library again, even though they're like control flow structures. The core library is automatically available. You don't have to require it. It's just magically always there. It's implemented as a C extension. It's a C extension that's just built into Ruby, but it's the same API it uses. And there's around 2,250 methods, so it's really large. There's a lot in Ruby's batteries included core library. So if we have something like a hash and we do .values, .sort, .first, .add, values, sort, first, and add are all provided by the core library. On top of that is the standard library. This needs to be required with some exceptions, but it's available without installing anything, so it's just there. It's part of the Ruby distribution still. We won't worry too much about the standard library in this talk. It's not really relevant. The code example here shows JSON, for example. So JSON.generate, that's a standard library feature. Something slightly interesting about it, though, is it's being lifted in the tower. So over time, the standard library is becoming a gem. It's being gemified and made something you can install separately if you wanted to. On top of this, you have your gems and your user code. This is Ruby code that's loaded at runtime from outside the interpreter, outside the Ruby distribution. It can be from a gem or it can be from code in your repo. That makes a big difference to us as programmers. We think about gems as being something separate from user code, but for the VM, it doesn't really make any difference. It's all code loaded from disk at runtime. So, for example, some Rails code and a controller, that's all user code. And sometimes gems and user code are written in C as well, right? A gem like Nokugiri or like OpenSSL, there's a lot of C code there. So it can still include C code, but it's required at runtime. There's many great things about core as it is. It's always available. It can't go wrong. You can't end up with the wrong version of core or find yourself without core installed. That's great. And it can be used to build bigger things because it's always available. So Ruby gems, for example, requiring gems, stuff like that, that's built on top of core. It's available instantly. As soon as the interpreter starts, it's just there, ready to go, which is great for application boot time. It can use VM internals to do things you can't do in Ruby. So a low-level thing like file I/O, that can't be done in pure Ruby, but it can be implemented in the core library with a file object. Compilers can be taught about it, and we'll explain more about that later because that's a key point. But there's bad things about core as it is. It's far too big, 2,000 some methods. That's too many methods for us to understand and to work with as VM implementers. There's no Ruby code that you can read, so you can't go and see what a method does with your knowledge of how to read Ruby and understand what the core library does. You're off into C code land, and it's not always the most understandable code, even if you understand C. There's no Ruby code you can debug. You can't step into it and understand what it's doing. There's no Ruby code to use profiling tools or coverage tools. It's all C extension code. And the bad thing about C extension code is, did you know C code can be worse for performance than Ruby code? We'll explain why later. And this problem gets worse as Ruby gets more sophisticated over time with things like YJIT. Can we get the best of the both worlds? So the best of the advantages without some of the disadvantages. What we're talking about doing is taking that core library part of the tower and splitting it up into two parts. One which we'll call the new core library implemented in Ruby. And that would be sitting on top of a smaller set of primitives which are implemented as they currently are in C or in Java in something like JRuby or TruffleRuby. Split it up into core and primitives. This should hopefully give us the best of both worlds. We'd have the bulk of our code in Ruby. We're Ruby programmers. We like seeing code in Ruby. We can understand it. This means it can be read, understood, debugged by anyone. It also means it can be better optimized by the VM. We're building things like YJIT to optimize Ruby code. So the more Ruby code we have it can optimize, the better. We'd have a small set of underlying primitives implemented in the same way as C extensions. And then we can teach the compiler specifically about them because there's a smaller set. So we can make the VM completely aware of this small set of primitives so it can work with them and understand exactly what they do. Ruby implementations already do this to some extent. MRI, also known as CRuby, does it just a tiny bit at the moment. JRuby does it a bit more, and TruffleRuby does it a bit more still. And we'll talk about Rubinius later, because there's some history here with Rubinius pioneering this technique. So let's talk about how MRI or CRuby does it to a little extent today. So this is from the MRI source code. It's a very simple method you might have heard of called tap. Tap allows you to run a block with a value and then return the value. You can use it to inject into like a pipeline of method calls to, for example, print out an intermediate value from a chain of method calls, something like that. It's very simple. And all it does is it yields its value and then it returns its value so you can keep using it. So we can express this in pure Ruby. And this is what MRI already does. There's no need for this to be written in C. So we have the kernel module written as pure Ruby code, and we have tap, and it just yields self, and then it returns self. We can understand that written in Ruby. And this is actual MRI code today. So part of Ruby's core is written in Ruby. A more complicated example is something like frozen. So you can ask an object if it's frozen. That's actually a method on kernel, which all objects include. So how can we implement that? Because of how can you read the frozen status if you're trying to implement the method call to read the frozen status? What MRI includes is something that lets you include C code in your Ruby code. And you can use this to write the lower level stuff you can't do in pure Ruby. So what we're saying here is I want to run the C code to call the C extension method RB object frozen P, P being like a question mark in Ruby. So this means that we can implement more stuff in Ruby because we can call into the C runtime code to do it. And then that lower level primitive is then implemented in C itself by directly accessing the objects, things like that. And the great thing is this method can be very small, this C function. It's only one line, it just gives us that tiny little bit of information. This is much better C code to have left in our Ruby VM after we've moved everything else out to Ruby. MRI has 2,194 core methods implemented in C. So the vast majority are still in C. It's got 64 core primitives, which is like a special kind of method implemented in C. Distinction doesn't matter too much. And it's got only 31 instances of that inline C. So it's a great idea. It's not being used much at the moment. It's got 7 special optimized core methods. Again, the distinction doesn't matter too much. And it only has 101 core methods implemented in Ruby. So it's only taking baby steps towards re-implementing stuff in Ruby. When we talk about some of the advantages and disadvantages, we'll see why that probably is right for the moment. TruffleRuby takes it quite a lot further. So TruffleRuby has the same methods that can be implemented in pure Ruby right now. So it has exactly the same tap method coming from MRI. And we can start to see one of the benefits here in that this code is exactly the same as MRI. So perhaps MRI, JRuby, and TruffleRuby could all start to share this code a bit. But TruffleRuby takes it much further. So the hash class, for example, has a couple of routines you might know about called key. That gives you the key for a value. It's like the opposite of looking up in a hash, right? It goes from the value back to the key rather than the key to the value. And when 2a gives you an array of tuples for each key value in the hash. So these can both be implemented on top of a primitive called each pair. So to get the key, to implement key, we can do each pair and then simply say if the value is what's expected, return the key, otherwise return nil. To do 2a, we can create an array and we can simply push each key value into it by using each pair. So we implement 2 methods in Ruby, nice and understandably, simple compiled code, and then we implement a single primitive, each pair, that does the heavy lifting. So one primitive gives us 2 Ruby methods. In TruffleRuby, there's 611 core methods implemented in Java, so we're using Java rather than C, and 353 core primitives implemented in Java. Again, it's just a slightly different type of core method. But we have 2,386 core methods implemented in Ruby. You may be wondering why this doesn't add up to 2,250. It's because there's helper methods and stuff like that. That makes it quite fuzzy. But the point is the majority of stuff is now implemented in Ruby instead of in Java. And we apply some techniques to think about, do we want something in Java or do we want it in Ruby to divide them up? JRuby does this technique as well. I'm not going to talk too much about JRuby because I don't want to speak on their behalf too much. But this is a great example from JRuby, integer times. So this is a routine you might know about. And again, this is a great simple implementation. It uses a while loop and yield to implement the times method. What are the advantages of doing our core in Ruby? One advantage is understandability. You can browse the Ruby code to understand it. If you know Ruby, you can go and see how the core library routine works. You can answer your own questions about what core methods really do. Does this method do this? Does it do that? You can try and read the documentation. The documentation isn't always great. If we have the core libraries written in Ruby, it's a single source of truth written in the one language that as Ruby programmers, we all share and all understand. You can use your normal debugger, coverage, and profiler tools. It's no longer a black box that's impenetrable written in C and a really esoteric version of C as well. Another advantage is we can share this code. MRI, TruffleRuby, JRuby, Artichoke, whatever comes next can all share the same core library. Each would implement just a smaller set of primitives their own way, so they can still do things differently to make it suit what they want to achieve, but they can share the core library on top, unmodified. VM people can focus on making the primitives work well, while the rest of the community worries about the core library and making that work well. It would mean that people were more free to make contributions to the core library based on what they know about from their application developer application development, and let the VM people worry about the primitives underlying it. A surprising benefit is going to be optimization. So we said that C code can sometimes be slower than Ruby code. Why is that? This is from the same key routine on hash. What we have here is in the middle, it compares the value against the expected value. So we do RB equal. Now that RB equal routine has to be able to handle comparing anything for equality because it's just static compiled C code. If we write it in Ruby instead, we can use the same techniques we use for optimizing Ruby, such as specializing for this case, I'm comparing two strings, and that's what I'll expect, and I'll optimize for that, and I'll generate special machine code for it. So it can end up being faster doing this stuff in Ruby than it would be to do it in C. There are some disadvantages of Ruby core, though. It's not an obvious choice that's got no downsides. It does have some disadvantages. The first one is parse time. We have to parse all this Ruby code at startup. So TruffleRuby has 2,000 methods written in Ruby. That means we have to load those 2,000 methods into the interpreter, adding on to the bulk of your application code. We said it's better for optimization, but that's only when the optimizations have had time to run. So those optimizations take time to apply while your application is running, and that means that it's slower to start with before it gets faster over time. People have already had to do things like disable equals gems. That turns off the support for Ruby gems for command line tools to reduce startup time, and this would make it much worse. So you may be familiar by a tool called Ruby Format by Fable. They had to disable Ruby gems in order to get faster startup time to make sure the command line interface wasn't too slow to be useful, and this would make it much worse. However, I think we can mitigate this. MRI embeds the YARV bytecode into the executable as data in the executable. It doesn't actually parse it, so the parser doesn't have to run. It can simply load that YARV bytecode. TruffleRuby goes even further. It embeds the objects generated by parsing the code into the executable. So again, it's not parsing it. This is really effective at mitigating it. TruffleRuby can actually start up more quickly than MRI in some situations due to this. And Benoit Deloze has a blog post about how this is possible. So again, this is actually counterintuitively, you think Ruby code would be slower. It's not. You think it'd be slower to start up. Actually, it could be faster. Another disadvantage is memory. Ruby code, although it's more compact on the screen, is bigger in memory than compiled C code, which is really compact. The profiles, inlining, and splitting, that's a technique I'll talk a little bit about later, and things that make Ruby code faster also take up more memory and ends up being potentially quite a lot more memory. And the optimizations we say that we get out of this also take memory to run. So the JIT compiler, things like that, that all takes memory and all adds up to being quite a lot of memory. Can we mitigate this? Actually, I don't really have any great ideas about how to mitigate that. Does anybody else? I'm open to ideas. It's an unsolved problem. At least it's per process, not per user, right? If you had a big VM instance, the cost is paid once. So if you can squeeze more users onto it, you can amortize that cost of that memory. There's an alternative we can use instead that TruffleRuby uses to run legacy C code, and that's Sulong. Sulong is an interpreter for C code. Now that sounds really counterintuitive. Isn't C a compiled language? There's no reason to divide languages between compiled and interpreted. You can interpret any language and you can compile any language with varying degrees of success. So Sulong is a C interpreter and it just in time compiles your C code. TruffleRuby uses it to run C extensions. It requires some truly heroic work to restore the performance of native C code, so it's very slow to start up. But it does mean we can optimize C code like that RB equal call. So there is one alternative, but it's pretty heroic to make it work. Here's a practical demonstration of how some of this stuff can work. So I've got a routine here called foo. It takes a hash and a value, and it uses that key routine we saw earlier. So it does hash.key, passing the value. I've got a hash, which contains A to 14. So I'm going to look up 14. I'm expecting to get the symbol A back. And then I have a loop. I run a loop in order to trigger just-in-time optimization and compilation, and I just call it with the hash and with 14. What I can do is I can ask TruffleRuby to explain to me how it's optimizing this and why. And we can see the benefits here. So what I've asked it to do is explain to me, what is it inlining in this case? Inlining is taking one method and inserting it into another dynamically so that you get a single method containing all your code and it can be all optimized together. What this tells me is it's starting to look at foo to inline stuff, and then it inlines hash key. Why can it inline that method? Because it's just more Ruby source code, right? The optimizations we wrote to teach the compiler about how to inline Ruby code into other Ruby code just work now for the core library. It's no longer a barrier to optimization. It's no longer a black box. But then it keeps inlining. We said we had that primitive, each pair, and it's inlined that as well. How is it able to do that? That's a primitive, not Ruby code. Well, because there's a smaller number of primitives now, we can teach the compiler individually about these primitives and about how to optimize those, how to inline those. And this could work in YJIT and other systems as well. And then actually it goes even further. So each pair, remember that primitive, it takes a block of Ruby code, and it can inline from that back into the Ruby code. So we get the benefits of being able to optimize the Ruby code, and because there's smaller number of primitives, we can optimize that as well. We can teach the compiler about it, and we get the whole thing optimized into one. And this is possible because we've written the core library into Ruby. So the benefits aren't just understandability. We can actually show we can get better performance out of this for the longer term. I'm a big fan of explaining what compilers are doing using a data structure called a graph. So I can tell the compiler, explain to me how you understand this program at a low level by telling me about your data structures. And this is a graph data structure. It's a flow chart, basically, of your program and all the operations. I don't want to go into a huge amount of detail on the specifics because it's fairly complicated, but I'll just zoom in. What we have here is the red arrows represent the control flow in the program. So from one operation to the next, like going from one statement to a next. And then the green arrows represent the data flow, so how the data flows through the program. And what we have here is we're showing that the return value flows from the load index at the top. The load index is loading the value from the hash. So what this is showing us here is we've achieved taking all that code, the user code, the core library written in Ruby, and the primitive implemented at a low level. We've taken that and combined it all into one single thing. That tower we had of different types of Ruby code, we've collapsed it into one. We've been able to compile it all together, optimize it together into something really low level, just reading from the hash to get the value out of it. And that's a fantastic achievement, and it's possible because of the core libraries written in Ruby. It wouldn't be possible if we had to teach the compiler about every single primitive like key, because there's not enough time in the world to teach the compiler about all of those. This makes it manageable. This is a potential way forward, I think, for Ruby. We could move the majority of core into Ruby. We'd leave behind a smaller, better defined set of primitives. We'd create a new version of Ruby that is like core Ruby that we could understand much better. And other programming languages do this at the moment. For example, Haskell has something called Haskell Core, which is much smaller and simpler. Everything can be expressed in it, but it's small enough to get inside your head and reason about, and to write tools to reason about as well. We could use TruffleRuby's substantial core as a starting point. We could teach our compilers and our static analysis tools, like our typing tools, our RubyConf, and things like that, more about these primitives, and then let it understand the rest of the Ruby code as it would your user code. This would give us a smaller, more manageable, more analyzable Ruby. But it works exactly the same now as for application developers. If you're just worried about using Ruby, you don't need to worry about it. It would work the same as before. Does it literally need to be a gem? I've pitched this as Ruby's core gem. I don't think it literally needs to be a gem. It could simply be bundled in the standard version of Ruby, but potentially we can make it so you can install a newer version if you'd like to. I want to give an attribution here to Rubinius. A lot of TruffleRuby's core library originated from Rubinius. That was an earlier implementation of Ruby, but it's been maintained by us, meaning the TruffleRuby team, for a few years now. So this is building on excellent work by Evan Phoenix, Brian Shirai, and many other people as well. Here's an even more radical idea, right? Ruby has this C extension API that people use to write C extensions. And obviously it's written in C. Could we implement those C extension library routines as Ruby as well? TruffleRuby does this today. So there's a core C library routine called RB str new frozen. And TruffleRuby implements that in Ruby. And what it does is the Ruby stub on the bottom right, that simply calls back into Ruby to run that routine. And we get the same benefits here. rbstr new frozen, you could look at the C code to understand what it does. That's quite complicated. You could try and read some of the documentation. That documentation isn't always great. Here, you can simply read it. What does it do? If the value is already frozen, it returns it. If not, it duplicates and freezes that new copy of it. That's great. We can understand it again, and it optimizes in the same way again. So we could go even further potentially. What conclusions can we draw from this? We've got this core of this tower of different parts of the libraries of Ruby. We can split the core library into core and rewrite it in Ruby and a smaller set of primitives on top. The part on the right-hand side would become the new shipped version of Ruby. And people who worry about Ruby implementation would just worry about those primitives, not the core on top of it. And someone else could worry about the core and what we want to do to expand that separately. Is it a good idea? Yes, there's tons of benefits. It's more understandable. It's more shareable, less work for the different Ruby implementations to do. It's more debuggable. You can use your standard tools. It's more optimizable by new tools like YJIT. It's more analyzable. So tools which look at typing and look for bugs and look for other problems can understand it more because it's more compact. There are some downsides. It might have an impact on startup time. We think we've got a solution for that. It may have an impact on memory usage. I'm not so sure we've got a great solution for that. So there's still some open questions. And it's surely worth trying. We've already got a core in TruffleRuby we could start trying this out with. It's going to become more relevant as MRI gets more sophisticated with things like YJIT. I think this could be a future of Ruby to build it into a direction that is higher performance, has better tooling, is better able to develop and adapt over time with a better core library. I want to give you some other things to check out if you're interested in this kind of work. So TruffleRuby is where this core library is implemented at the moment. Sorry for the long URL, but I encourage you to go and look at the core library implemented in Ruby. It's just Ruby code. We all know Ruby here. You can all read it and understand it. graalvm.org/Ruby is the official TruffleRuby website, and my work's all at chrisseaton.com/TruffleRuby. A lot of this optimization I've said is possible is down to a technique called splitting. This is a really powerful, sophisticated optimization that we're bringing to Ruby in TruffleRuby. And Benoit Deloze has a talk today at 3 p.m. in room A, and I encourage you to go and watch. People are doing academic research on top of some of these ideas. This is a paper that Sophie Kaliba has just published. It's called, what she does is she analyzes what call sites and calls look like in Ruby, and she shows how powerful our optimizations in TruffleRuby are for optimizing Ruby code. And that would apply to the core library as well. So I'll encourage you to go and Google for this paper and have a read of it. I said something about Rubinius. Rubinius was Ruby implemented in Ruby. As well as the core library implemented in Ruby, at one point they were writing much of the VM in Ruby. Did you know that their garbage collector was at one point written in Ruby? You may know the term mark sweep as a type of garbage collector. This is the sweep routine from Rubinius implemented in Ruby. What it says is for each object, if the object has been marked by the mark phase, then leave it alone, otherwise deallocate it. And again, isn't that nice and understandable? If you go to rubycompilers.com/Rubinius, you can read about the history of Rubinius and how it did this and where its core library came from. And finally, I want to publicize another side project of mine. It's called the Ruby Bibliography. If you're a fan of reading about Ruby research and stuff like that, this page lists all the Ruby research that is out there. That's the end of my talk. Thank you very much. I think we've got 2 minutes for questions if anyone would like to ask one. So the question is, how do we decide what primitives do we have? And there's trade-offs either way, and how would the implementations agree which primitives? That's a great question. I think that's another open issue we'd have to work on to resolve. What we do in TruffleRuby is we implement stuff in Ruby by default, and then we create a primitive instead if we've got some compelling reason to. But the compelling reasons are different based on how you implement Ruby. So TruffleRuby, for example, has different ways of implementing hashes based on how you're using them. And therefore, we have a different set of primitives that would make sense if you had a more simple hash like MRI does. So I don't have a great solution to that. That is another open problem that we'd have to work and resolve. But the great thing about we've already got a working core library, we could start from that point of it working and then adjust those sort of primitives over time. Yeah. All right, I'll leave it there. Come and find me if you've got any questions afterwards. Thank you very much.